This video is going to give you another example of conditional probability. So this is kind of a new slide to the course packet relative to what was in my previous video where I used some PowerPoint, but I think it's good to see another example of this. So recall what conditional probability is. So conditional probability is really about having a little bit of extra information. This is the way we write a conditional probability. It's the probability of A given B. So the additional information is this B thing. So we've been told that B occurs. Now we want to reevaluate whether we think A is going to occur given that additional information. And we have this formula that gives that to us. Now we've been doing conditional probabilities for over a week. The row and column percents that we talked about around crosstabs were really just conditional probabilities. So let me carry through with this row and column percent business to show how what we're doing now is just a very natural continuation of what we did last time. So consider some population. Let's say we have only 1,000 people in this population to keep the numbers nice and round. And some of these people in the population are buyers of my product. Some are not buyers of the product. So in my example, it looks like there's 100 people in the population of 1,000 who buy from me. So 10% of this population is made up of buyers. 90% are made up of non-buyers. Now, very often in marketing, what we want to do is find other variables that relate to whether or not a person buys from our product. So this is really common when you're trying to buy media. Often you'll use a demographic proxy like age or income or gender to help locate media where you're likely to find eyeballs interested in your product. So to keep things really simple, let's use gender as a possible variable. And suppose that we have 600 males in this population and 400 females in this population. Now we have 20 buyers who are male. We have 80 buyers who are female. Then the remaining 580 men are non-buyers. The remaining 320 women are non-buyers. Now what I'm taking you through here is nothing new. It's just a plain old crosstab like we did last week. We could ask, for example, within the total, so the total refers to all 1,000, what percentage of people are male buyers? Okay, so the answer would be 2%. So let me go over that one more time. We could say 2% of everyone in the population is male and a buyer. So that number comes from taking 20, dividing by 1,000. Likewise, we could say that 58% of the entire population is a male non-buyer. 8% of the population is a female buyer. 32% is a female non-buyer. Where does that 32% come from? Well, it's 320 divided by 1,000. Okay, so those are the percent within the total. I've started calling those numbers joint probabilities. So that percent within total is the joint probability. Now we could also look at this within gender. So let's restrict our universe to only females now. So what percentage of females are buyers? Well, 80 out of the 400 females are buyers. 80 divided by 400 is 20%. So we could say that 20% of females are buyers. Likewise, we could say 3.3% of males are buyers. So that's a review of crosstabs, and just note the important difference between these two numbers. This is 20% of females are buyers. This number is 8% of the entire population is female and a buyer. Now let's convert this into our new notations. So we'll let B be the event that a randomly selected person from this population is a buyer. So therefore, the probability of B is 100 over 1,000. So that is simply that marginal probability that's given in the table up there. Likewise, if F is the event that a randomly selected person from this population is female, the probability of F is 40%. So that is simply this number. Take 400 over 1,000 and you get that number. We could also consider what is the chance that a randomly selected person from this population is both female and a buyer. Well, let's see. There are 80 female buyers. Divide by the size of the population, which is 1,000, and that gives us 8%, which is right here. And now in Chapter 6, we call that a joint probability. So joint probabilities involve this and symbol, the intersection. Now let's go to additional information. So instead of just looking at everyone, we could restrict our universe. So for example, let's restrict our universe to females. So what is the probability that a female, given this extra piece of information that the person is female, what's the chance that that person is a buyer? You could say, what is the probability of buying given female, given that it's a female? Well, let's go plug this into our formula up here. So we go look at that formula, and it's going to be 0.8 divided by 0.4. That's the way we would do it in Chapter 6. Earlier, last week, we would have said, well, we have 80 divided by 400, and that's 0.2. So the chance of a female, if I told you it's a female, what's the chance that female's a buyer? Well, it's 20%. Notice that that is greater than the chance of just being a buyer, which was 10% up here. Here's a little exercise for you to do. Let's move on to independence. So independence is closely related to conditional probabilities. Let's start with what independence is. So what independence tells us is that additional information doesn't help. So if two events are independent, additional information about one of those events doesn't help at all. So the way we could express this notion that the additional information doesn't add anything new is as follows in symbol. So we could say that the probability of A occurring, given this extra piece of information that B has occurred, doesn't change the probability of A occurring. So that's one way to express it. You could also say, well, additional information about A doesn't change the probability that B will occur. A third way of expressing it is a little bit less intuitive, but we'll often use this when we have independence. And so the joint probability is just the product of the marginals. Let me give you an example of this. So let's go back to my little population of 1,000 people, and we're going to break it out differently. So instead of breaking it out by men and women, let's say that some of the people in this population have green hair, and then the remaining people don't have green hair. So I'm going to say that 200 people out of the population have green hair, 800 don't. Now the other thing I'm going to tell you is that 20 people with green hair are buyers. 80 people without green hair are buyers. Now, from this, we can get all of our percentages. So it looks like there's a 10% chance that a randomly selected person from the entire population is a buyer. So that's 100 out of 1,000. Likewise, we can say that, well, 10% of people with green hair are buyers. Where did that number come from? Well, it's this 20 divided by the 200, and you get 10%. So let's look at our formulas. The probability of buying is still 10%. The probability of having green hair is 200 out of 1,000, or 20%. And the probability of both having green hair and being a buyer is 2%. All right, so let's now compute the conditional probability of buying given that somebody has green hair. So this is just the joint probability divided by the marginal. So 2% divided by 20% is 10%. Now notice that this is 0.1, and that's just the probability of being a buyer. So my point here is that the additional information of green hair, so if I tell you the probability of buying given green hair is 10%, that doesn't change the probability of just buying, of anyone buying. So this additional information doesn't help. Therefore, we say that buying is independent of the hair color in this example. That's quite a bit different than the female variable, where notice the additional piece of information that a person is female doubles the probability that they are a buyer.